The paper presents a novel, fully discrete numerical scheme for simulating the dynamics of magnetization and displacement in magnetoelastic materials within the small strain regime. This is achieved through a coupled system of partial differential equations, comprising the Landau Lifshitz Gilbert (LLG) equation for magnetization and the conservation of linear momentum law for displacement. The interplay between these two equations is nonlinear, with the effective field in the LLG equation influenced by mechanical stress, and the strain in the momentum law dependent on magnetization. A key challenge lies in the non-convex pointwise constraint on the magnetization, which must be a vector field of constant unit length. To address this, the authors employ a decoupled integrator based on first-order finite elements in space and an implicit one-step method in time. This approach allows for unconditional convergence of the discrete approximations towards a weak solution of the system as the mesh size and timestep size tend to zero. The proposed method does not require a nodal projection to enforce the unit length constraint on the discrete magnetization, eliminating the need for weakly acute meshes for stability. Numerical experiments validate the theoretical findings and demonstrate the applicability of the scheme for simulating dynamic processes involving magnetoelastic materials at submicrometer length scales. This work contributes to the advancement of computational micromagnetics and the study of magnetoelastic effects, with potential implications for the development of new technologies leveraging these phenomena. This paper introduces a generalized PDE system for studying magnetoelastic materials, encompassing both volume and surface forces, as well as a more comprehensive expression for magnetostrain. Building upon previous models, this system enables the description of a broader class of magnetoelastic materials. The proposed integrator is based on first-order finite elements in space and an implicit first-order timestepping method, similar to previous studies. However, it diverges from these by removing the nodal projection from the magnetization update, following other research. This modification avoids the requirement of weakly acute meshes but introduces a controlled violation of the unit length constraint on the magnetization at mesh vertices, dependent on the timestep size. The analysis demonstrates unconditional well-posedness, a discrete energy law, unconditional stability, and unconditional convergence of the approximations towards a weak solution of the problem. Under a restrictive CFL condition, the discrete energy law can be passed to the limit, resulting in an energy inequality for weak solutions. The key contributions of this paper are threefold. 1. It considers a more general setting than previous studies, including volume, surface forces, and a more general magnetoelastic contribution. 2. The proposed integrator is energetically mindful, with approximations satisfying a discrete energy law that resembles the continuous problem's energy law. And 3. The convergence proof is constructive, providing a new proof of existence of weak solutions for a more general model of magnetoelastic materials in the small strain regime. A novel numerical scheme is presented for simulating magneto-mechanical systems, focusing on the interaction between magnetic and mechanical fields in ferromagnetic materials. The model problem is defined in a bounded Lifshitz domain omega, with the boundary split into two parts, gamma d and gamma n. The magneto-mechanical state is described by displacement and magnetization vector fields, U and M, respectively. The total strain epsilon consists of elastic strain epsilon L and magnetization-dependent magnetostrain epsilon M, where epsilon M is given by epsilon M equals Z. M circled times M, with Z being a fourth-order, minorly symmetric tensor. The elastic part of the strain epsilon L is related to the stress tensor sigma through Hooke's law, sigma U M equals C epsilon L U M, where C is a fourth-order, fully symmetric, positive definite stiffness tensor. The elastic energy EL is defined as the sum of the energy associated with the compatible strain, the work done by a volume force F, and the work done by a surface force G on the boundary gamma n. A new numerical integrator is introduced, designed to solve the system of partial differential equations describing the evolution of the displacement and magnetization fields. This integrator is shape-regular, allowing for the use of general mesh generators. The main results of the work are presented, along with numerical experiments demonstrating the effectiveness of the proposed scheme. The appendices provide definitions and results from linear algebra and discuss how to derive the dimensionless setting from the fully dimensional model considered in the physics literature. The Heisenberg exchange contribution to the magnetic energy is captured by equation 2, a simplified representation of the total free energy. The total free energy is comprised of magnetic and elastic energies, as defined by equation 3. The system's dynamics are governed by the coupled system of the conservation of momentum law and the Landau Lifshitz Gilbert (LLG) equation, subject to initial and boundary conditions. The LLG equation incorporates the Gilbert damping parameter, which ensures the decay of the system's kinetic energy. The energy law, as described by equation 8, reveals that both total energy and kinetic energy decay over time, with the decay rate modulated by the Gilbert damping parameter. Additionally, the elastic tensor is assumed to be uniformly positive definite, as described in equation 9. This assumption is crucial in understanding the system's behavior, as it influences the dynamics of the magnetic and elastic energies. A weak solution to the initial boundary value problem is defined as a pair, U, M, that satisfies certain conditions. Specifically, U and M must comply with spacetime variational formulations of the problem's equations, which inherently enforce the boundary conditions. Furthermore, the initial conditions must be met in the sense of traces. A key aspect of these weak solutions is that they adhere to an energy law, analogous to that satisfied by strong solutions. This energy law is a fundamental principle governing the problem's behavior. The magnetostrain, a crucial concept in this context, is expressed as a general formula encompassing various forms found in literature, including the cubic case. This formulation provides a unified framework for describing the magnetostrain, which is a critical component in understanding the underlying physical phenomena. The design of the numerical method for the coupled system begins with the simplification of neglecting the lower-order contributions of magnetic energy, whose numerical integration is well understood. Time discretization involves a uniform partition of the time interval, with discrete time derivatives defined accordingly. Space discretization includes the mesh size, triangulation, and the definition of piecewise affine and globally continuous functions. This approach maintains a highly technical and professional tone, utilizing precise language and domain-specific terminology suitable for the field. The finite element space S1, Th, cubed and the set Mh, delta are defined, consisting of approximate magnetizations Mi_h that satisfy the constraint, phi h, z, is greater than or equal to 1 for all z element of Nh, with an L1 error controlled by delta. When delta equals 0, the set Mh, 0 is obtained, where the unit length constraint holds at the vertices of the mesh. A nodal projection operator pi h is introduced to map Mh, delta to Mh, 0, ensuring the unit length constraint at the mesh vertices. The discrete tangent space kh, Mi_h, is defined, enforcing the orthogonality property partial differential Tmi_h equals 0 at the vertices, a crucial requirement for solutions to the Landau Lifshitz Gilbert (LLG) equation. The Moss-Slumped L2 product, H, a scalar product on S1, Th cubed, is recalled. This product is used in the fully discrete numerical scheme proposed to approximate solutions to the initial boundary value problem. The decoupled algorithm for the LLG equation with magnetostrain consists of three main steps. First, the discrete tangent space kh, Mi_h, is used to compute v_h, an approximation of the time derivative of the magnetization. Next, the new magnetization Mi+1_h is updated using v_h. Finally, the updated displacement ui+1_h is computed using the new magnetization. This algorithm, similar to the decoupled algorithm proposed in 14, uses discrete initial data m0_h, u0_h, and u0_h, which are suitable approximations of the initial conditions. The key novelty lies in computing the new magnetization first and then the updated displacement at every time step. The authors present a computational framework for solving the coupled system of equations governing the dynamics of magnetoelastic materials. Algorithm 4.1, a fully linear method, requires the solution of two linear systems per time step. It employs the tangent plane scheme to compute the new magnetization, discretizing the Landau Lifshitz Gilbert (LLG) equation, and the backward Euler method for the conservation of momentum law. The algorithm's well-posed-ness is proven, ensuring stability and convergence for every theta element of 1/2, 1. A discrete energy law, derived in equation 23, demonstrates that the algorithm conserves energy, with dissipative terms due to the damping parameter alpha and discrete energy dissipation d, h, k. This dissipation is composed of three parts: exchange energy, kinetic energy, and elastic energy variation. The nodal projection is implemented for all approximate magnetizations, excluding those in the exchange field, cross-product, and update step, allowing for a fully linear algorithm despite the nonlinearity of the LLG equation and its coupling with the conservation of momentum law. This framework is crucial for simulating the complex behavior of magnetoelastic materials under various external stimuli, enabling accurate modeling and prediction of their response and paving the way for further investigations into their properties and potential applications. The authors present the energy dissipation analysis of algorithm 4.1, a crucial step in establishing the stability and convergence of the numerical scheme. Equation 25 represents the discrete energy law, where the right-hand side consists of two parts: the artificial damping term d, h, k and the error term a, h, k. The artificial damping term arises from the implicit treatment of the exchange contribution of the effective field and the use of the backward Euler method. The error term is due to linearization, decoupling, and the use of nodal projection to impose the unit length constraint on magnetizations. The authors remark that their argument to show proposition 4.3 for algorithm 4.1 can be transferred to the algorithm of 14, resulting in a discrete energy law for that algorithm as well. However, the counterpart of equation 23 in 14 is only an inequality, and its proof requires the assumption of a weakly acute mesh, and the error term a, h, k does not include the last two terms in equation 25. The authors then discuss the stability and convergence of algorithm 4.1, assuming the approximate initial conditions converge to the exact initial conditions as the mesh size decreases, as stated in equation 26. They show that algorithm 4.1 is unconditionally stable and that the error in the unit length constraint can be controlled by the time step size, as stated in proposition 4.5. The proposition provides bounds on the discrete energy norm, including the kinetic energy, elastic energy, and the error in the unit length constraint, as shown in equations 27 and 28. The threshold K0 and the constant C depend only on the shape regularity parameter of the mesh, problem data, and the uniform bounds of the energy of the approximate initial data. In the realm of computational fluid dynamics, the convergence of sequences towards a weak solution to the initial boundary value problem is a critical concept. This process involves the approximation of complex fluid flows using numerical methods, which are essential for understanding and predicting various phenomena in physics, engineering, and other fields. A key theorem in this context states that if certain conditions are met, such as the CFL condition, then the sequence of approximate solutions will converge to a weak solution of the initial boundary value problem. The CFL condition, named after Courant, Friedrichs, and Louis, is a necessary condition for the stability of numerical schemes used in solving partial differential equations. It dictates that the speed at which information can travel in the numerical solution must not exceed the physical speed of wave propagation in the system being modeled. The theorem also implies an energy inequality, which provides a quantitative measure of the error between the approximate and exact solutions. This inequality is crucial for assessing the accuracy and reliability of the numerical methods employed. However, it is important to note that this method has its limitations and assumptions. One such assumption involves the use of the nodal projection, a technique used to project the initial data onto the finite element space. This projection can lead to inconsistencies if not handled properly, particularly when dealing with non-smooth initial data. Furthermore, the convergence theorem relies on certain regularity assumptions about the solution, which may not always be satisfied in practice. In such cases, additional techniques or modifications to the numerical scheme may be necessary to ensure convergence. Despite these challenges, the convergence theorem remains a cornerstone in the development of numerical methods for solving fluid dynamics problems. Its implications for the energy inequality offer valuable insights into the behavior of complex systems, making it an essential tool for researchers and practitioners in various fields. The authors of the research paper present a series of numerical experiments to demonstrate the applicability of their algorithm, which has been implemented using the NetGen-NG-solve package. The solution of the constrained linear system in the algorithm is based on the nullspace method, solved using GMRES with an incomplete Lou decomposition preconditioner. The elastic equation is solved using a Jacobi preconditioned conjugate gradient method. These experiments utilize material parameters estimated for FeCO-CB, including mass density, Gilbert damping parameter, exchange length, stiffness tensor, and Lamé constants. The magnetostrain is modeled using the expression in equation 13. In some experiments, the magnetic energy is supplemented with the Zeeman energy, modeling the interaction of the magnetization with an applied external field. The material parameters used are reported in Table 1, including the exchange constant, Gilbert damping parameter, gyromagnetic ratio, permeability of free space, saturation magnetization, saturation magnetostrain, density, gravitational acceleration, and Lamé constants. The authors then present two numerical experiments showcasing the capability of the algorithm to simulate physical processes involving magnetoelastic materials. The simulation object is a bar of FeCO-CB, clamped at one end, with a physical length of 20 times the exchange length and width, height of 6 times the exchange length. The maximum mesh size is approximately 0.9 times the exchange length, ensuring that it is below the exchange length. The details of the experiment setup are presented in the following sections. The research on page 12 delves into the experimental setup and results of section 5.2, which investigates the direct and inverse magnetostrictive effects. In the direct magnetostrictive effect, a uniform external magnetic field is applied along the plus y direction, and the dynamics are observed through the magnetization and displacement components. The results clearly demonstrate a coupling between magnetization and displacement, with the magnetization aligning with the applied field and the displacement mirroring magnetization changes. Figures 2 and 3 illustrate the time evolution of the average magnetization and displacement components, respectively, showing an increase in the y and z components of magnetization and displacement with stronger applied fields. The energy evolution consistently decreases with increasing applied field strength. In contrast, the inverse magnetostrictive effect involves a traction applied on the y equals 20 plane in the plus y direction, which leads to a decrease in the z component of magnetization with increasing traction. Figure 4 displays the time evolution of the average displacement and magnetization components under different traction values. This section's findings highlight the interplay between magnetic and mechanical properties of the material, providing insights into the complex dynamics involved. The time evolution of the average magnetization and displacement components is examined under varied applied magnetic fields, as illustrated in Figure 2. The total energy over time is also presented for different magnetic field strengths, shown in Figure 3. A key aspect of this experiment is the investigation of the parameter theta, which governs the degree of implicitness in numerical simulations. By analyzing the data, the research aims to elucidate how theta influences the behavior of the system under different magnetic field conditions. The results reveal that the parameter theta significantly affects the system's behavior, particularly in the presence of strong magnetic fields. As theta increases, the implicitness of the numerical simulations also increases, leading to distinct changes in the magnetization and displacement components. Notably, the total energy of the system exhibits a marked dependence on theta, with higher values of theta resulting in increased energy fluctuations. The findings have important implications for the development of accurate numerical models that capture the complex behavior of magnetic systems. By understanding the role of theta in controlling the implicitness of simulations, researchers can refine their models to better predict the response of magnetic materials to external fields. This, in turn, can inform the design of novel magnetic devices and materials with tailored properties. Ultimately, the study highlights the critical importance of carefully calibrating numerical simulations to ensure accurate predictions and optimal performance in magnetic systems. Figure 4 presents the results of a simulation experiment, as described in section 5.2.2, demonstrating the time evolution of average magnetization in displacement components for varied traction strengths. The simulation utilizes material parameters for Φ-CB, with a Gilbert damping parameter set to alpha equals 0.001. The initial condition for the magnetization is a hot magnetic state, where vertex values are randomly assigned and normalized, while displacement and its time derivative are initialized to 0. The simulation is run for 1 × 10^11 seconds with a time step size of 1 × 10^15 seconds, exploring different values of theta element of 0.50000005, 0.505, 0.6, 0.7, 0.8, 0.9, 1. The figure displays the average magnetization components mx, mi, and mz in plots A, C, and the average displacement components ux, uy, and us in plots D, F. These plots illustrate the impact of varying traction strengths on magnetization and displacement components. Notably, the treatment of the exchange contribution in equation 19 influences the results. Maintaining the unit length constraint on the magnetization, a fundamental property of the Landau Lifshitz Gilbert (LLG) equation at constant temperature, is ensured by algorithm 4.1, as stated in proposition 4.5, particularly equation 28, which bounds the L1 norm of the magnetization by a constant Ck. The authors also observe that deviating from a theta implicitness parameter of 1/2 can lead to significant artificial numerical damping, detrimental in certain situations, such as long-time simulations. This is evident from the energy decreasing behavior shown in Figure 5, where greater theta values are associated with more energy loss. The experiment in section 5.3.1, involving a hot magnet, demonstrates that the unit length constraint is violated at most linearly in time when measured in the L1 norm. This violation is evident through the time evolution of the total energy for different values of theta, as depicted in Figure 5. The constraint violation, measured as the left-hand side of equation 28, is plotted against the time step size k in Figure 6a. The results show that the error decays linearly in k, as predicted by equation 28. The constraint violation is of the order 10 to the power of 2 for k on the order of 10^3 due to the hot initial state of the magnetization. In Figure 6b, the L-infinity norm of the magnetization at the final iterate is plotted against the time step size k. This figure illustrates how the maximum nodal value of the magnetization evolves with varying time steps. The nodal maximum appears to decrease as the time step size increases, indicating a more stable solution for larger time steps. These experiments provide insight into the stability and convergence properties of algorithm 4.1 under various conditions. They highlight the importance of choosing appropriate time steps to maintain the unit length constraint and achieve desired stability in the numerical solutions. In the verification of constraint violation inequalities, a simulation is conducted where the magnetization at a node may undergo multiple rotations. The L-infinity norm of the magnetization at the final iterate is plotted against the time step size k, demonstrating that the nodal maximum numerically tends to 1 as desired, although the decay is nonlinear. The energy law robustness of the algorithm is investigated by examining its behavior with respect to discretization parameters. Simulations are performed using various mesh sizes and time steps, revealing that energy decay occurs for all combinations. Notably, the decay is slower for smaller time steps, indicating that the algorithm exhibits energetic robustness under the specified conditions. These results highlight the algorithm's ability to maintain energetic stability despite variations in discretization parameters, making it a promising approach for simulating complex magnetic systems. The nonlinear decay of the L-infinity norm of the magnetization underscores the importance of considering the interplay between time step size and mesh size in ensuring the accuracy and robustness of the simulation. Numerical experiments and mathematical proofs supporting the claims made in Section 4 are presented in this section. Figure 7 displays the time evolution of the total energy for different values of h and k, which corroborate the claim that Theorem 4.6, E, is not needed. The proofs of the results presented in Section 4 are collected here. To facilitate understanding, well-known results are recalled, including the norm equivalence of the Moss-slumped L2 product, induced by parallel H, which satisfies parallel phi H parallel is less than or equal to parallel phi H parallel H is less than or equal to square root 5 parallel phi H parallel for all phi H in S1, Th, 3, as stated in equation 29. Additionally, the error estimate, phi H, psi H phi H, psi HH, is less than or equal to CH2 parallel nabla phi H parallel nabla psi H parallel for all phi H. Psi H element of S1, Th, 3 is recalled, derived from 11, lemma 3.9. Local inverse estimates are also presented, stating that for all k element of Th and 1 is less than or equal to R, P is less than or equal to infinity, we have parallel phi H parallel LP, K, is less than or equal to CH3, RP, PR, K parallel phi H parallel LR, K. For all phi H in S1, Th, 3, as shown in equation 31, referenced from 11, lemma 3.5. Furthermore, the LP norm of functions in S1, Th, 3 is equivalent to the LP norm of the vector collecting their nodal values, weighted by the local mesh size, as stated in equation 32. This equivalence is bounded by C-1 parallel phi H parallel LP, omega, is less than or equal to n airy summation z element of NHH3z, phi H, z, p, 1, p is less than or equal to c parallel phi H parallel LP, omega, for all phi H in S1, Th, 3. The authors discuss the well-posed-ness of algorithm 4.1, a crucial step in establishing the stability and convergence of the proposed numerical method for solving the Landau Lifshitz Gilbert equation in micromagnetics. They define a family of bilinear forms and linear functionals, utilizing the discrete elastic field and magnetic field, to demonstrate the positive definiteness of these forms. This leads to the existence and uniqueness of solutions for the discrete problems in both displacement and magnetization terms. The proof follows a similar structure as presented in 14, with additional terms related to the magnetic field incorporated into the analysis. The discrete energy law satisfied by the iterates of algorithm 4.1 is a central focus of this research. The law is derived by demonstrating the equivalence of equation 21 to the statement A2, UE plus 1H. Psi H equals lead 2, psi H, for all psi H in the space S1D, Th, 3. This equivalence ensures the existence and uniqueness of a solution UE plus 1H within S1D, Th, 3. The discrete energy law is subsequently proven by combining equations and exploiting the finite dimensionality of the problem. This involves strategically selecting test functions and leveraging the inherent properties of the algorithm. The mathematical derivations underlying this proof are crucial, as they reveal novel insights and significant findings. The significance of this discrete energy law lies in its ability to provide a rigorous mathematical framework for understanding the behavior of algorithm 4.1. By establishing a precise energy law, this research provides a foundation for further analysis and development of numerical methods. The precise mathematical derivations and proofs presented in this work contribute to a deeper understanding of the underlying mechanisms governing the algorithm's behavior. The refined version begins by emphasizing the importance of direct and concise narration, ensuring that the content is easily understood by both expert researchers and stakeholders. Maintaining a highly technical and professional tone, the summary will use precise language and domain-specific terminology to convey complex concepts and methodologies. In order to ensure accuracy, the summary will cover all major points from the original text, including key terms, concepts, and methodologies. This will involve explaining equations, algorithms, and mathematical concepts in detail, as well as summarizing information from figures, tables, and graphs efficiently. The refined version will also highlight novel ideas, significant findings, and important arguments presented in the original text. This will include discussing any limitations, assumptions, and future work mentioned in the paper. To maintain continuity, the refined version will connect to content from previous pages where applicable. It will start directly with the content and end without any concluding remarks or metacommentary, avoiding the use of first-person pronouns or phrases. Overall, the refined version aims to provide a clear, concise, and technically accurate summary of the research paper, making it accessible to a wide range of audiences. The stability of algorithm 4.1 is discussed in this section, focusing on unconditional stability and estimating the violation of the unit length constraint. The authors break down the proof into several lemmas. Lemma 6.2 provides L2 bounds for the approximate magnetizations, stating that for every integer 1 is less than or equal to j is less than or equal to n, there exist constants C1 and C2 greater than 0 such that the L2 norm of the approximate magnetization is bounded by a sum involving the previous magnetizations and the shape regularity parameter. Additionally, an estimate for the L1, omega, norm of the difference between the approximate magnetization and its norm is provided, also bounded by a similar sum. In lemma 6.3, the authors estimate all quantities involving the magnetization, showing that for every integer 1 is less than or equal to j is less than or equal to n, there exists a constant C3 greater than 0 such that the sum of the squared L2 norm of the gradient of the magnetization, the squared L2 norm of the previous magnetizations, and the squared L2 norm of the gradients of the previous magnetizations is bounded by the sum of the squared L2 norm of the initial gradient of the magnetization and a term involving the squared L2 norm of the previous magnetizations and their gradients. This estimate is crucial for proving the unconditional stability of algorithm 4.1. These lemmas contribute to the overall proof of proposition 4.5, which demonstrates the unconditional stability of algorithm 4.1 and provides an estimate of the violation of the unit length constraint. The authors employ lemma 6.1 to estimate the term involving the elastic field, yielding inequality, 34, which bounds the inner product of the magnetization and the elastic field. This estimate is then used to derive an upper bound for the sum of the norms of the magnetization and the elastic field, a crucial step in the proof of the main theorem. Next, lemma 6.4 is presented, demonstrating the Lifshitz continuity of the magnetostrain with respect to the magnetization. This result is essential for establishing the stability of the numerical scheme. The proof leverages the boundedness guaranteed by the nodal projection and the norm equivalence stated in 11, lemma 3.4. Furthermore, lemma 6.5 provides an estimate for the time derivative of the displacement and the elastic strain, a key component in the energy stability analysis of the numerical scheme. The proof involves summing up the estimates from 0 to J1, starting from equation 36, in the proof of proposition 4.3. Throughout these lemmas, the authors meticulously manage the constants and dependencies on the problem data, shape regularity parameter of the mesh, and other parameters, ensuring the accuracy and robustness of the numerical scheme. This careful management is critical in maintaining the reliability and efficiency of the proposed method. The authors derive an estimate for the term involving the magnetostrain, a crucial component in the analysis of the problem. Starting with the energy identity, they apply lemma 8.5 and rearrange terms to obtain an expression linking the energy norm of the solution and the magnetostrain term. The magnetostrain term is then estimated using a telescoping series argument, yielding an upper bound involving the energy norm of the solution, magnetostrain, and time step. This bound is further refined by lemma 6.4, which provides a bound on the time derivative of the magnetostrain. The final estimate combines the bounds on individual terms, including the energy norm of the solution, magnetostrain, and forcing terms. The estimate is proportional to the energy norm of the solution in magnetostrain, and inversely proportional to the time step. Additionally, a bound on the forcing terms is provided, which is proportional to the norm of the forcing functions and inversely proportional to a small parameter delta, used to control the contribution of the forcing terms to the overall estimate. The stability and convergence analysis of algorithm 4.1, a key component in solving parabolic equations, is presented. To establish convergence, the authors first prove a stability estimate for the discrete problem, combining Poincaré's and Korn's inequalities with the discrete Gronwall lemma. This stability result is crucial for demonstrating the convergence of the algorithm. The proof begins by applying lemmas 6.2, 6.3, and 6.5 to derive an estimate that combines various terms related to the discrete solution's energy, including time derivatives, elastic energy, and mesh size. This estimate shows that the discrete solution is uniformly bounded in certain norms, allowing the extraction of subsequences with suitable convergence properties. To complete the convergence proof, the authors follow a standard argument used in proving the existence of weak solutions for parabolic equations. They identify the limit of the subsequences as a weak solution of the problem, thus demonstrating the convergence of algorithm 4.1. The proof also addresses the partial omission of the nodal projection by borrowing ideas from previous works. A novel energy estimate plays a crucial role in the analysis, providing a comprehensive understanding of the stability and convergence properties of algorithm 4.1. This rigorous analysis highlights the potential of algorithm 4.1 as a reliable numerical method for solving parabolic equations. The lemma begins by establishing an estimate for the LPA norm of the difference between the approximate magnetizations generated by algorithm 4.1 and their nodal projections. This is achieved through a proof that starts by showing an estimate for the LPA norm of the difference between the approximate magnetizations and their nodal projections. The proof utilizes the norm equivalence and convexity properties of the LPA norm to derive the estimate. This estimate is then used to conclude the proof of the lemma. The lemma's findings are crucial for the subsequent development of the research, particularly in the context of time reconstructions and their stability. The authors establish convergence results for subsequences of UHK, MHK, and VHK as k approaches 0. Specifically, UHK converges weakly to U in H1, omega t, strongly in L2, 0, t, H1, omega, and L2, omega t, and weakly star in L infinity, 0, t, H1, omega, as stated in equations 45a-45d. Similarly, UHK and UHK converge to U in L2, omega t, and L infinity, 0, t, H1, omega, respectively, as shown in equations 45e-45f. The sequence MHK is proven to converge weakly to M in H1, omega t, strongly in L2, 0, t, H's, omega, for all S in 0, 1, and pointwise almost everywhere in omega t, as demonstrated in equations 45g-45 meters. Furthermore, VHK converges to partial differential Tm in L2, omega t, as stated in equation 45n. The proof relies on the boundedness results from proposition 4.5, which enables the extraction of weakly and weakly star convergent subsequences. Interpolation theory results from 15 are utilized to establish the compact embeddings H1, omega t, H's, omega t, and the continuous inclusions H's, omega t, subset of L2, 0, t, H's, omega. The same convergence results are also obtained for the sequences UHK and MHK. Notably, the authors highlight the significance of the quantity in equation 46, which involves the differences of MHK, UHK, and their time derivatives, in the context of the convergence results. This quantity plays a crucial role in understanding the asymptotic behavior of the subsequences as k approaches 0. The Landau Lifshitz Gilbert equation is a fundamental model in micromagnetics, and its weak solutions are crucial for understanding magnetization dynamics. This paper establishes the convergence of a sequence of approximate solutions to a weak solution of the Landau Lifshitz Gilbert equation. To achieve this, the authors introduce piecewise constant time reconstructions for the approximate magnetizations and derive convergence results in various spaces, including L infinity, 0, t, H1, omega, L2, 0, t, H1, omega, and L2, omega t. These results are essential for identifying the limit of the sequence with a weak solution of the Landau Lifshitz Gilbert equation. The proof begins by demonstrating the uniform boundedness of the sequences, UHK, and U plus or minus HK, in L infinity, 0, t, L2, omega, and L2, 0, t, H1, omega, respectively. By exploiting the compactness of the embedding L2, 0, t, H1, omega, subset of L2, 0, t, L2, omega, the authors extract subsequences that converge weakly in L2, 0, T, L2, omega, and strongly in L2, 0, T, L2, omega. This implies that the limits of the subsequences coincide with the function U constructed earlier. Next, the authors define the piecewise constant time reconstructions m plus or minus hk and establish their convergence properties. These sequences are uniformly bounded in L infinity, 0, T, h1, omega, and converge weakly in L2, 0, T, h1, omega, and strongly in L2, omega t. The convergence of the products m plus or minus hk circled times m plus or minus hk in m plus or minus hk circled times m plus or minus hk to m circled times m in L2, omega t, is also proven, which is crucial for the proof of theorem 4.6, Finally, the authors identify the limit, U, m, with a weak solution of the Landau Lifshitz Gilbert equation by leveraging the convergence results established in the previous lemmas and the definition of the weak solution. This culminates in the proof of theorem 4.6, which demonstrates the existence of a weak solution to the Landau Lifshitz Gilbert equation under the given assumptions. The proof of theorem 4.6, involves applying lemma 6.7, yielding the desired convergence properties for the subsequences of the discrete solutions. This shows that the limiting functions u and m satisfy property I of definition 2.1. Property E is established using available convergence results, the continuity of the trace operator, and assumption 26 on the discrete initial data. To demonstrate property E, it is necessary to show that u and m satisfy the variational formulations 10 and 11, respectively. This involves similar modifications as in a previous work. Proposition 6.9 states that the iterates of algorithm 4.1 satisfy the discrete energy law, 48, which is a variant of proposition 4.3. The discrete energy law, expressed in terms of the nodal projection of the magnetization approximation, involves the discrete energy A. The proof of proposition 6.9 is omitted, as it is similar to that of proposition 4.3. The discrete energy law, 48, provides a bound on the energy of the system at each iteration, with terms d, h, k and a, h, k representing dissipation and energy contributions, respectively. This energy inequality has significant implications for the stability and convergence of the numerical method. To prove theorem 4.6, we start by summing equation 48 for I equals 0, J1, which yields an estimate involving the discrete time derivative of U, the discrete Laplace operator, and the discrete gradient of M. Applying the Cauchy-Schwarz inequality, the weighted Young inequality, and lemma 6.4, we refine this estimate to include terms related to the discrete energy difference and the discrete gradient difference. To estimate K, 4, we employ the Cauchy-Schwarz inequality, Holder inequality, and classical inverse estimates, resulting in a bound that depends on the discrete time derivative of U, the discrete gradient of M, and the discrete Laplace operator. This bound also involves the discrete energy difference, the discrete gradient difference, and the LP and LP norms of VH. Similarly, we estimate K, 5 by utilizing the Cauchy-Schwarz inequality and the discrete energy difference. The resulting bound depends on the discrete time derivative of U, the discrete gradient of M, and the discrete Laplace operator, with additional terms related to the L2 norm of VH and the discrete energy difference. Crucially, these estimates establish the desired bounds for the discrete time derivative of U and the discrete gradient of M, which are essential components of the proof of theorem 4.6, These bounds demonstrate the convergence of the discrete solutions to the continuous ones as h right pointing arrow 0, under certain assumptions on the initial data and the regularity of the solution. Estimating the difference between consecutive terms in a series is crucial for stability analysis. This estimation relies on the equality between two expressions, one involving the difference between consecutive terms and another involving the sum of products. To bound this term, inverse estimates and lemmas are employed. The resulting expression is complex, comprising dissipative terms, stability conditions, and original series terms. Notably, this expression is bounded by a series of terms involving the difference between consecutive terms, stability parameters, and original series terms. The estimation process is underpinned by the application of inverse estimates, which provide a robust framework for bounding the term of interest. The lemmas, in turn, offer a rigorous foundation for the estimation, ensuring the accuracy and validity of the results. The final bound, comprising a series of terms, provides a comprehensive characterization of the system's stability properties. The stability analysis of the system is heavily reliant on this estimation, as it provides critical insights into the system's behavior and response to perturbations. The bound, encompassing the difference between consecutive terms, stability parameters, and original series terms, constitutes a fundamental aspect of this analysis. This research paper presents a comprehensive analysis of the Landau Lifshitz Gilbert equation with magnetostrain, focusing on its numerical approximation and convergence properties. The authors utilize a finite element method to solve this complex problem, which is crucial in understanding the behavior of magnetic materials under various conditions. The paper begins by introducing the mathematical model of the Landau Lifshitz Gilbert equation, which describes the dynamics of magnetic fields within materials. It then outlines the finite element method used for solving this equation numerically, emphasizing the importance of choosing appropriate test and trial functions to ensure accuracy and stability of the solution. The authors also discuss the CFL condition, a necessary criterion for ensuring that the numerical scheme is stable and convergent. A detailed proof of the energy inequality is provided, a key result in establishing the convergence of the finite element approximation. This proof involves using the energy functional associated with the Landau Lifshitz Gilbert equation and applying weak lower semi-continuity arguments. In addition, the paper highlights several previous studies on the Landau Lifshitz Gilbert equation, including works by Alujas, Bartels, and Bonas, among others. These studies have contributed significantly to our understanding of the equation's properties and its applications in various fields of physics. The paper concludes with a discussion on the implications of the findings and potential future directions for research. It emphasizes the importance of further investigations into the numerical methods for solving the Landau Lifshitz Gilbert equation, particularly in the context of micromagnetism and spintronics. Numerical methods are essential for solving nonlinear partial differential equations, which are ubiquitous in modeling complex physical phenomena. One such phenomenon is magnetostrain, the coupling of magnetic and elastic properties in materials. This coupling leads to nonlinear partial differential equations that require robust numerical methods for accurate solutions. Finite difference methods, a popular approach, discretize the spatial and temporal domains, approximating derivatives using finite difference operators. However, these methods can be limited by numerical dispersion and dissipation, which can compromise solution accuracy. An alternative approach is the finite element method, which offers greater flexibility in handling complex geometries and boundary conditions. The Galerkin method, a variant of the finite element method, projects the nonlinear partial differential equation onto a finite-dimensional subspace, enabling the solution of the resulting algebraic system. Another approach is the discontinuous Galerkin method, which combines the advantages of finite element and finite volume methods. This method is particularly effective in capturing sharp gradients and discontinuities in the solution. Spectral methods, which expand the solution in terms of orthogonal basis functions, can provide highly accurate solutions for problems with smooth solutions. However, they can be limited by the Gibbs phenomenon, which arises from the truncation of the infinite series. The choice of numerical method depends on the specific problem, with each method offering trade-offs between accuracy, computational efficiency, and implementation complexity. The selection of an appropriate method is critical, as it can significantly impact the accuracy and reliability of the solution. In the realm of linear algebra, a fourth-order tensor A is defined by its components iom. The tensor can be classified as minorly, majorly, or fully symmetric, depending on the relationship between these components. A's transpose is also introduced, which has implications for symmetry. The appendix outlines various operations involving tensors, including double contraction. This operation is crucial when dealing with 4 tensors, 2 tensors, and 1 tensors. These mathematical frameworks are essential for understanding the research presented in the paper. The definitions and identities provided in the appendix serve as a reference for researchers to understand the complex mathematical concepts used throughout the work. This includes the conditions under which a tensor is considered symmetric, as well as how the transpose of a tensor affects its symmetry properties. The double contraction operation is a key concept in this context, allowing for the manipulation and combination of tensors of different orders. This operation is fundamental in the research, enabling the authors to derive new insights and results from their data. This section provides a comprehensive overview of the mathematical tools employed in the research, making it an indispensable resource for those seeking to fully grasp the methodologies and findings presented in the paper. In the context of ferromagnetic materials, this research paper discusses various mathematical identities and their applications. The Frobenius product of two matrices, denoted as μ, is defined as a scalar given by the sum of the products of corresponding elements of the matrices. The tensor product of two vectors, m and w, is also defined as a two-tensor m circled times w, where each element is the product of the corresponding elements of m and w. The paper then presents lemma A.4, which provides an identity for manipulating magnetostrain terms. This identity involves a minorly symmetric 4-tensor Z, a symmetric 2-tensor sigma, and two 1-tensors m and w. The lemma states that the Frobenius product of the transpose of Z and sigma, when contracted with m and w, is equal to the Frobenius product of sigma and the contraction of Z with the tensor product of m and w. This result is useful for simplifying expressions involving magnetostrain terms. Next, the paper introduces lemma A.5, which is useful for demonstrating the stability of numerical schemes. This lemma provides an identity involving a sequence of vectors, nu(i), in an inner product space. The identity relates the inner product of the difference between consecutive terms in the sequence and the current term to the norms of the current and previous terms, as well as the norm of their difference. Finally, the paper discusses the non-dimensionalization of variables for a ferromagnetic body occupying a volume omega in R³. The total strain epsilon, U, is defined as the symmetric part of the displacement gradient, while the magnetostrain epsilon m, is defined as the contraction of a minorly symmetric 4-tensor Z with the tensor product of the magnetization m and itself, normalized by the saturation magnetization Ms. These definitions are essential for understanding the mechanical and magnetic properties of ferromagnetic materials. The total energy of the system, encompassing the kinetic energy of the magnetization, interaction energy with an external magnetic field, and elastic energy stored in the material, is a fundamental concept in understanding the dynamics of magnetic materials. The Landau Lifshitz Gilbert, LLG, equation describes the precession of the magnetization vector around the effective field, providing insight into the temporal evolution of the magnetic state. This equation is coupled with the conservation of momentum equation, which details the dynamics of the displacement field. A crucial concept in this context is the exchange length, used to scale spatial variables and displacement. This scaling leads to a set of dimensionless equations that are more convenient for numerical simulations. These equations provide a powerful tool for researchers to simulate and predict the behavior of magnetic materials under various conditions, shedding light on their complex dynamics and potential applications. In essence, the interplay between magnetic and mechanical properties in these materials can be understood through the interdependence of the LLG equation and the conservation of momentum equation, with the exchange length serving as a key parameter for simplifying the analysis. This refined understanding opens up new avenues for the development of advanced magnetic devices and technologies. We have arrived at the dimensionless model problem, the foundation of our work. To simplify notation, we assume kappa equals 1 and neglect the applied external field, unless explicitly stated otherwise. Additionally, we omit the primes from dimensionless quantities, a convention followed in sections 26 to streamline our notation. This framework enables us to delve into the complexities of the problem at hand.